Okay. Bienvenidos a esta sesión del seminario permanente de teoría de continuos e hiperespacios. En esta ocasión tenemos una invitada especial que ha sido varias veces expositora plenaria en congresos internacionales como el Spring Topology. Ella es Daria Michalik, del Instituto de Matemáticas de la Universidad Jan Kochanowski en Polonia. Ella es profesora asistente de este Instituto de Matemáticas. Hizo un trabajo para su doctorado en geometría, en topología geométrica. Su tesis fue supervisada por el profesor Henryk Torunski, y el trabajo que nos va a presentar hoy es un trabajo conjunto con el profesor Bodek Karatonik, y también tiene trabajos conjuntos con el profesor Alejandro Llanes y con la profesora Verónica Martínez de la Vega. El año pasado fue galardonada con el premio Miniatura Grant por el Polish National Science Center. Y estará acá en México en junio-septiembre por 4 meses en la UNAM. Thank you, Daria. Welcome to the seminar in Toluca. And please.
Okay, so first of all, I would like to thank you for invitation. And this is great pleasure for me to give a talk in your seminar. Okay, do you see my screen?
We can see.
Okay, thank you. Well, okay, so today I would like to talk about confluent projections and connectedness on inverse limits for set-valued functions. And this is joint work with Bodek Karatonik, and all results came from the paper published in last year in Rocky Mountain Journal of Mathematics. Okay, so at the beginning, let me recall some basic definitions. By xi, I mean a continuum, and by continuum, I mean a compact connected metrizable space. And let fi be the single valued map from xi plus 1 to xi. So we have a sequence of continua, and by inverse limit of this sequence, I mean these points of Cartesian product of xi's such that xi is the image of xi plus 1 by fi. So this is when we are talking about a single valued map. During my talk, I will talk mostly about a multi-valued functions, and if fi from defined onto xi plus 1 to xi is a multi-valued function, then inverse limit of this sequence, it is again the set of points from the product, Cartesian product of xi's, but now xi is contained in the image by fi of xi plus 1. Okay, and during my talk, I will assume that all multi-valued functions are upper semi-continuous. So let me recall that a function is upper semi-continuous at point x, if and only if for every open v in y containing the image of f of x, there exists an open u contained in x, containing x, such that for every t in u, we have image of t is contained in v. Okay, the definition is a little bit complicated, but what we will use many times is this characterization of upper semi-continuous functions. So if X is Hausdorff space and Y is compact, and F is a multivalued function from X to Y, then F is upper semi-continuous if and only if graph of F is closed set in the Cartesian product of X times Y. This is a very useful characterization, and we will use it many times. Okay, so interesting question and very natural is if an inverse limit preserve if inverse limit of continua is a continuum. So the question is if inverse limit preserves compactness and connectedness. And if we are talking about compactness, we have following theorem. Suppose that XIFI is a sequence of upper semi-continuous functions of compact Hausdorff spaces, then inverse limit of this sequence is non-empty and compact. So inverse limits preserve compactness. So with compactness, there is no problem. And what about connectedness? If we have a sequence of maps of continua, so if we have sequence of single valued functions, then again, inverse limit of this sequence is connected. So for single valued maps, and just for maps, inverse limit of maps preserves connectedness as well. But unfortunately, when we are talking about multi-valued functions, we have problem. And look at this picture. This is graph of multi-valued function f from inter-unit interval into unit interval, and it is a very well-known example of map between intervals such that the inverse limit is not connected. It is not very difficult to prove that this set n, this is a subset of inverse limit with first coordinate equal to 1/4, second 1/4, and third 3/4, is an open and closed in the same time subset of inverse limit. So inverse limit is not connected. So we have very easy example of multi-valued function with connected graph even, such that inverse limit is not connected. Okay, but there are also some positive results with some more assumption about these functions f. We have what we want to have. So if XIFI is a sequence of upper semi-continuous function of continua, and Fi are continuum valued functions, so the image for each point is a continuum, then inverse limit in such a case is a continuum, is compact and is connected. So this, if the image for every point is continuum, then inverse limit is a continuum. Of course, at this example, inverse images of some points are 2 points, so it is not, of course, continuum. Well, this result of Ingram and Mahavier was generalized by Van Nal, but let me define some new. Let me introduce some new definition. We say that if f is multi-valued function, then f satisfies Vn condition, Vn because Van Nal, if there is a family f alpha, where alpha are in A, of continuum valued functions f alpha, such that f is the union of f alpha. So we can represent f as the union of continuum valued functions f alpha. And what is very important, the functions f alpha are defined on whole space X. Okay, and are of course also upper semi-continuous. And Van Nal proved that if X is a continuum and F it is a map from from X onto X, and this is multi-valued upper semi-continuous function, such that graph of F is connected and F satisfies the Vn condition for each. Okay, there shouldn't be this for E equal to 1 and 2. Sorry. Then inverse limit is connected. So if graph of F is connected and F satisfies the Vn condition, then inverse limit is connected. And first remark is that instead of you use all the time the same space X and the same map function F, we can take different xi's and different functions fi, and the theorem is still true. So it can be a little bit generalized by this remark. Okay, but take a look at this example one more time. So we know already that inverse limit is not connected. Of course, the graph of this function is connected. So why this function f is not the union of some continuum valued functions? And the reason is that this graph contains these two hands. These hands are too short, and f is not the union of a continuum valued function because of these two hands. And the same problem of too short hands appear when we are talking about confluent maps. Maybe let me recall definition. So map F is confluent if for each subcontinuum Q of Y, each component of the inverse image of Q is mapped by F onto Q. This definition was introduced by Janusz Haratonik, and this is a common generalization of open and monotone maps, but probably you know it very well. So what is not confluent in this situation? Of course, the projection from graph of F onto X is not confluent because of these two short hands. Okay, and we observed with Włodek this fact, and we try to generalize it. And this result just generalize our earlier observation. So if a multi-valued function f from x onto y satisfies a Vn condition, then the projection px from graph of f onto x is confluent. Okay, so now I would like to show you the sketch of the proof of this result. So let us assume that f from x onto y is a function with Vn property. So this is the union of continuum valued functions f alpha. Okay, and let q be continuum in x, and let xy be a point in a graph of f such that x is contained in q. And now we need to find a continuum p contained in a graph of f with these two properties. The point xy is contained in p, and the projection onto x of p is equal q. Okay. Function f satisfies the Vn condition, so there is alpha in A such that y is contained in f alpha of x, because point xy is contained in graph of f, and the graph of f is the union of graphs of F alphas. So there is alpha such that Y is contained in the image of X by F alpha. Well, so now we can define our continuum P as the union of all images F alpha of X where X is contained in Q. And I think this picture, you can see everything very well on this picture. And P is it is not very difficult to see that P is a continuum. We use here upper semi-continuity of F alpha, and the fact that graph of F alpha is closed. And we use also here the fact that Q is a continuum, and F alpha is continuum valued map function. Okay, so we find P with this property with that projection onto X of P is equal to Q. So we are done. And natural question is if this theorem is also true in inverse direction. So is it true that if the projection is confluent, then the map satisfies Vn condition? And we have to assume something more about our continuum X. Namely, if X is an arcwise connected continuum and the projection from graph F onto X is confluent, then function F satisfies the Vn condition. So we have to assume that our continuum X is arcwise connected. Okay, well, I would like to show you now the proof of this theorem, maybe the sketch of the proof, because with all details it is rather long. So let P of X is the projection from graph onto X, and assume that it is confluent. So and take a point x0, y0 from graph of F, and to show that F satisfies the Vn condition, it is enough to construct a continuum valued function G from X onto Y such that Y0 is contained in image of X0 by G, and G of X is contained in F of X for every X in X. Okay, so define the set D. D is a set of all continua of X with this property that X0 is contained in D, and there exists a continuum valued map GD from D onto Y such that Y0 is contained in the image of X0 by GD, and GD of X is contained in F of X for every X in X. So D is a set of continua with required properties. We would like X belongs to D. Okay, and now we can show using the Kuratowski-Zorn lemma that there is maximal element M in our set D. Okay, so if M is equal to X, we are done, because there is if M is equal to X, there exists a continuum valued map defined on whole space X with required properties. Okay, so let us assume that M is not equal to X. By arcwise connectedness of X, we know that there exists an arc E and a point P0 in M such that M intersected with E, it is just exactly a point P0. Okay, so look at this picture. Let me recall that the GM is a is a continuum valued function defined on M by definition, because M is an element of D. So we have a continuum valued map defined on M, and we have arc E and common point P0. Okay. Since P of X, since projection from graph of F onto X is confluent, there is continuum A in the graph of F such that projection onto X of A is equal to E. And what more? Point P0, Q0 is contained in A intersected with graph of GM for some Q0 contained in Y. So now we have graph, we have continuum A union graph of GM, but map defining of M onto M union E is not continuum valued. So it is not good. We have to work a little bit harder. What we can do? We can divide the arc E into two arcs, E0 and E1, such that E0 intersected with E1 is a point P1 for some P1 contained in E. So we divide this arc into two pieces, and because our function f is projections from graph onto X is confluent, so there are two subcontinua A0 and A1 of graph of F such that Px of A0 is equal to E0, projection of A1 onto X is equal E1, and there is a point Q1 in Y such that P1 Q1 is contained in the intersection of E of A0 and A1. So observe that, of course, only in our picture, the union of graph of GM and A0, it is a graph on continuum valued function with domain M union E0. So we have, of course, only on our picture, because the situation in general can be more complicated. But we have there is a bigger continuum with required properties. Okay, but if we take union of graph of GM with A0 and with A1, it doesn't work anymore, because there are points in E1 such that the image of these points are not connected. So we have to work a little bit harder. So what we can do? Okay, we know that the union of A0 and A1 is a continuum such that projection onto X of A0 union A1 is equal to E, and P0 Q0 is contained in the union of E0 and A1. And put P0 is equal to A, our first continuum A. P1 is equal to the union of A0 union A1, and know that projection of P0 and projection of P1 is equal to E. And in the same way, we construct arcs E00, E01, E10, E11 in X, and continua A00, A01, and so on in graph of F, and continuum P2 as the union of this continua A, such that projection of P2 is equal to E. And we can continue in the same way. And finally, we obtain a sequence P0, P1, P2 of continua in our graph, in graph of F, such that Px of Pn is equal to E for every n, natural n. Okay, so now let us take P as the limit of convergent subsequence of P0, P1, and so on. And we conclude that projection of P onto X is equal to E, and that GM union P is a graph of a continuum valued function with the domain union M and E. But this is contrary to the maximality of M. M was maximal element in our family D, and here we just proved that M union E is has also desired required properties. So we have contradiction. So M is just whole space X, and we are done. Well, let me show you an example showing that assumption of arc-wise connectedness is essential. I want to show you that there is a map, there is a function f such that projection from graph onto X is confluent, but it is not the union of our function f. It is not the union of continuum valued maps. Okay, so let X be a sin curve with limit interval, and let f be a multi-valued function from X onto interval. So in this situation, graph of f is contained in the Cartesian product of X times interval. So the graph of f is contained in this space. Okay, let me define our function f. So this is definition, but of course it is much easier to see this function on a picture. So as I told, the graph of f is contained in X times interval. And the graph of f in this picture, these green lines are the graph of f. So if the first coordinate of X is not equal to 0, then we just have a value 0. We just mapped all points onto 0. And for X equal to 0, we have 2 points in image, also 0, but also the points lying on this the second line, second interval. Okay. So our graph looks like that. And of course, it is not difficult to see that projection from graph onto X is confluent. When we are thinking about this right side of the picture, this projection is just identity map. So it is of course confluent. And when we look at this left side of the picture, this limit side, there is this projection. We have these 2 intervals, but this projection onto bottom is also, of course, confluent. So the projection is confluent, and why it is not the union of why f is not the union of continuum valued functions? Let me assume that f is the union of continuum valued functions. Okay. And of course, all functions f alpha are defined on whole space X. And observe that for every alpha in A, all points from the graph of f with first coordinate bigger than 0 is contained in graph of f of alpha. Okay, where are these points with first coordinate bigger than 0? Of course, they are on the right side of our picture. So in this part of our picture, there is no other choice. Every f alpha has be the same as f. Okay, so in this right part of the picture, every f alpha is the same as f, function f. And look, and what about this left side of the picture? By the closedness of graphs, we know that for every alpha of E, all points with last coordinates equal to 0 is also contained in graph of f alpha. Because f alpha is upper semi-continuous, so it has closed graph. So this limit interval on level 0 in our picture has to be contained in graph of f alpha. Well, look now at this point P here. This point P here doesn't belong to the graph of union of f alpha because it doesn't belong to any graph of f alpha, because all of f alpha, because for every alpha, this interval in the bottom, in the level 0, belongs to graph of f alpha, and f alpha are continuum valued functions. So this point P doesn't belong to the graph of the union of f alpha. But of course, this point P belongs to the graph of f. And this is contradiction because graph of f is equal to graph of union of f alpha if the f has Vn condition. So we have contradiction. Okay, so we can see that assumption of arc-like connectedness is essential in our proof, and also we can see that assumption that projection from graph onto X is confluent is more general than Vn property. And that's why it is a very interesting problem if the Van Nuys theorem remains true if we replace the assumption of Vn condition by the more general assumption of the confluence of projections from graph Fi onto Xi. Van Nuys condition, we know that is true if each Fi satisfies Vn condition, but maybe it is also true if each f alpha has confluent projection from the graph. Okay, so I think it is a good time to finish my talk, and this is a bibliography of our paper. There are 3 well-known books and papers of Ingram and Mahavier, and paper of Van Nuys containing this theorem about connectedness of inverse limit. Okay, thank you.
Thank you, Daria. Is there any question? ¿Alguna pregunta para Daria?
David, I have a question.
Okay.
What happened in the case when your example was in the Euclidean 3-dimensional space? What happened, or there is an example in the plane with the same characteristic or something like that?
I don't know an example in plane. We just concentrate on this one example, and we didn't think more about that. And it's a very interesting question.
Just because you have a lot of possibility to move in the Euclidean space.
Of course, it's true.
But in the plane, maybe we have some problems to move the function.
Yes, that's true.
Okay, thank you.
Thank you for interesting question.
¿Alguna otra pregunta? No, no hay preguntas. Bueno,